Hi there. My name is Jason Gu, and during the summer after my junior year of high school, I spent around 5 weeks living on Purdue University's campus. There, I worked in the lab of Professor Raphael Lang, performing research with the worldwide XENON dark matter search collaboration. For future reference as well as documentation, I thought I'd take some time today to review the work I accomplished during my 5 weeks, as well as future potential steps in our project. So to begin, the Xenon collaboration is based on the abundance of historical evidence for dark matter, or matter that's invisible to us. From things like galaxy rotation curves and gravitational lensing, strong evidence suggests that there is much more mass in our solar system, galaxy, and entire universe than what meets our eyes and what we can see through telescopes. Xenon searches for this matter using a dual-phase time projection chamber, using both gaseous and liquid xenon to hopefully detect scintillation or light flashes from particle interactions, namely from the hypothesized dark matter particle called the weakly interacting massive particle, or WIMPs for short. So my research mainly revolved around what is known as the dark box there at Purdue, which is located in the Asterix lab, which is a lab that seeks to replicate a miniature version of the larger Xenon N-ton detector that's being constructed right now, an upgrade from the previous Xenon 100 detector. Now, the dark box is exactly what it sounds like. It's a box that tries to minimize the amount of light that enters it. It does so by having tight latches on all sides, as well as thick foam padding surrounding the interior. So, namely, the end goal of the entire project with the dark box was to test for the potential scintillation, or once again, light emitting properties of a coolant named Novec 7000, which potentially could be implemented into future detectors if it were to scintillate. Now, the method by which I accomplished this was through the use of photomultiplier tubes, or PMTs, which are light sensors that are sensitive to single photon events. These PMTs operate due to the photoelectric effect. So when light enters a PMT, it emits electrons from a metal plate called a dynode, which rapidly multiply to become a current pulse, which can be recorded, stored, and collected as data. However, due to the thermoionic emission of electrons, or just the random expulsion of electrons due to it being in room temperature, these PMTs can create signals in the complete absence of light, creating what are known as dark counts. While these are random and essentially unavoidable, the rate at which these dark counts are produced is measurable, and characterizing the dark count rates of our lab's PMTs was the first step in my dark box project. So to do this, I used a photomultiplier tube connected in the dark box to a super high voltage or SHV supply, as well as an oscilloscope which can detect potential differences across a handset trigger value. So the plot to the right here is the result of 300-second or 5-minute long datasets taken with an oscilloscope at multiple trigger values, creating a function of the calculated dark count rate as a function of the amplified voltage, or 10 times of the actual voltage produced by these dark counts. Before taking a look at this actual plot, let's discuss the general expected shape of the graph that we would predict. So when the trigger value is extremely high, many of the dark counts would not produce a signal strong enough to be triggered on the oscilloscope. Thus, the calculated dark count that we would have is essentially zero. However, as we begin to lower our trigger value on the oscilloscope, we would begin to collect more and more of these dark counts until we would eventually approach a horizontal asymptote, which would represent the true dark count rate of our photomultiplier tube. Finally, after reducing the trigger value on the oscilloscope to a point so low that we can actually detect electronic noise produced by the oscilloscope and the voltage supply, the calculated dark count rate would essentially skyrocket to infinity and would no longer be representative of our true dark count rate. So taking a look at our plot in these lime green points here, we can see that the general trend actually matches perfectly with our expectations, with an asymptotic value of a dark count rate of 25 Hertz, or 25 dark counts per second. Researching past detectors, the PMTs used in previous Xenon detectors, like the Xenon 100 detectors, used PMTs with dark count rates of around 50 Hertz. So with this comparison, I successfully discovered that our PMTs in the Asterix lab were comparable, if not better functioning, than those used in previous detectors, giving our research group the confidence to continue to future steps testing with these PMTs. However, one further test that needed to be done before starting to take real data with our liquid Novec 7000 was to measure the gain of our PMT, or the potential difference value that would provide the most visible and revealing data in future tests. In order to do this, I created a Jupyter Hub Python script that analyzes the number of counts of all PMT events or signals, not just dark counts, as a function of a complex unit that's analogous to the energy of the pulse that's created. So on the slide now are two plots that are made using the script. One with a PMT connected with 700 volts to this super high voltage supply, and another with 750 volts. So these tall green peaks shown are the result of 300-second long or 5-minute long data sets taken in the dark box with nothing else in it but a PMT. Now, as we can see, these peaks are centered very closely around an energy level of 0, which when we repeated the test with a uniforming flashing light or an LED, when we placed it in the dark box, we got these resulting curves in pink here, which are not centered around 0. So the explanation for why these green peaks are centered around 0 is because the only events being collected in a completely dark box are electronic noise and dark counts, which have random energy levels which would obviously average to something like 0. However, these pink peaks are what are known as single photon peaks, which are produced by the LEDs, revealing the presence of light. And our intended signal of scintillation and particle interactions in the PMTs will be light as well. So we want to make these pink peaks as visible as possible from the green peaks. And we can see that in the 700 volts, the pink peak is kind of hiding behind the 700, and if the colors were not distinguished, we may not be able to tell the difference. However, at 750 volts, this pink peak here is a lot more visible. And due to this, I concluded that 750 volts should be used for all future testing with these PMTs to maximize what's called the gain of the PMT, to make these light interactions as distinct as possible from the irrelevant green noise peaks. So with these preliminary steps taken, I was ready to begin developing a process by which we could test the potential scintillation properties of the Novec 7000 that we discussed earlier. To do this, I first hand-built an apparatus which can suspend a PMT over a beaker of liquid, as shown here. With the setup completed, though, I didn't have much time in my stay at Purdue left. However, I did begin trying to collect data for different liquids in the beaker, namely an empty beaker, a beaker of water, as well as a beaker of Novec 7000. To catalyze any potential scintillation light flashes, I used a cobalt-57 radioactive source that would interact with liquids demonstrating scintillation properties, and I hope to collect these light signals that were produced inside of the PMTs that I tested. Throughout the testing, though, I ran into an extremely frustrating yet crucially revealing issue, and that was that the dark box was in fact not completely dark, with the plots that I made revealing a large light peak, like the one we showed before with the LED, in the complete absence of light and in situations where I would not expect light at all, for example, an empty beaker with no radioactive source. I reported this fact to my professor and research group in my final presentation, and they are currently working to devise strategies to fix this issue as we speak. So to conclude, there's a couple main takeaways that the research I completed last summer reveals. First, that the PMTs were performing at a quality comparable or better than those of previous detectors and could easily be used for future testing after I've left. Also, I concluded that 750 volts would be an optimal voltage for testing future use as well. And finally, that the dark box was unfortunately not completely in the absence of light, and that this was a pressing issue that future volunteers and researchers who worked on campus must seek a solution to. On a more personal note, these 5 weeks were extremely insightful to me, giving me a first glimpse into the professional physics academia world that I really hope to pursue in the near future as a career. I'd like to give a huge thank you to Professor Lang for providing such a great opportunity and hospitality to me and accommodating me as the only high schooler to ever work in his lab, as well as all the graduate students and postdoctoral researchers on campus who were extremely helpful and enthusiastic to guide me in my research as well as around campus when I got lost. Overall, I hope you've gotten a little bit of an instructive overview of my work at Purdue, and thank you for watching.